I think we're ready to start. That's been welcome. This is second session in week 7, and we did start chapter 11, and this is section 11.2. In this section, I will introduce the infinite series. Okay, that's when we did learn about the sequences. Now we will try to add something. Actually, add is a good addition, is a good terminology. And we will create an infinite series. So let's see what we have. We know what sequence is. Sequence is just the list of numbers. Yeah, that's when we will have a term, like list of terms. A sub 1, A sub 2, A sub 3, 4, 5, and so on. Now what we will do, as I said, we will be adding the terms of the sequence. Okay, that's when we will be, not just like comma, not like the list of the terms, we will have addition of all of these terms. That means A sub 1 plus A sub 2 plus A sub 3 and so on, A sub n. Okay? And what we will create? We will create an infinite series, or just the series. I don't know if my pronunciation is good, but we know what I'm talking about. Okay, that means that's how the series is defined. Okay? And we will try to do stuff with the infinite series. We will try to, of course, look at the sum, and we will probably think like it's maybe, I don't want to say pointless, but maybe we're thinking this way, that adding infinitely many terms, we will always like accumulate huge number, right? We will always have like infinity, or we actually know the terminology, the series will be divergent if we're getting a huge number, right? But let's see, let's investigate. And we will use a sigma notation, right? I think you probably learned this also yesterday. Adding similar terms, instead of like writing, having the expanded form, like A sub 1, A sub 2, A sub 3, I can use the sigma notation. That means sigma, the symbol sigma is telling me that I am adding these terms. Underneath the sigma, we have the beginning, the initial value. This means that I have to go from 1 to infinity, and always n means the positive integer, the natural numbers. Okay, that means n, it's like a counting number. 1, 2, 3, and so on. Okay? Not like no fractions, no negatives. Occasionally, you have to be careful. We may add 0. Okay, we may add 0. 0 is not a counting number, because if I will count, like even the students in the classroom, I will not say 0. I will say 1, 2, 3, 4, and so on. Okay? That means this means that I am adding A sub 1 and then plus A sub 2 plus A sub 3 and so on. That means I can define this like that. That means that's the sigma notation, that's the expanded form. Okay, let's keep moving. What else we have? And just what I mentioned, yeah? Does it make sense to talk about the sum of infinitely many terms? Yeah? Are we gonna have like a finite number ever? We don't know. Okay, let's check this out. Okay. It would be possible to find the finite sum of the series. Okay? But let's take something like that for now. N, adding like a sigma from 1 to infinity, and just having n means counting numbers, okay? Natural numbers, 1, 2, 3, 4, 5, and sigma is telling me that I have to add 1 plus 2 plus 3 plus 4, and so on. That means, what do you think? This sum exists as a finite number? Of course, I have to keep going. Or do you think this will be like an infinity? Huge number. You can probably think like adding 1 plus 2 plus 3 plus 4 plus 5 plus, I don't know, 1000, 1001. we definitely creating a huge number. That means this finite sum, this sum, this infinite series doesn't exist as a finite sum. I do have a formula, okay, maybe you remember from Calc 1 or even from like pre-calculus, adding the finite counting numbers, I can always use this. That means if I will ask you to add 100 numbers from 1 to 100, you can put 100, 100 plus 101, divide by 2, for example. Or if we will keep n as an infinity, of course, this expression at infinity is also infinity. Right? That means this will be big number. But what we have to notice, okay, and what this will be one of the way to define, because we will not always have this nice formula. I can write it down. Limit Sn is infinity, n plus 1 over 2, of course, is infinity. Okay? Oh, I still want to box it. Because having an expanded form or sigma notation, as I said, we will never, no, not always, we will have this nice formula. Okay, but what we will try to do, we will try to create something like cumulative sum. In order to check how the infinite series behaves, I have to create a partial sum. That means taking just one term, we will call S sub 1, okay, which this is 1. Now, taking two terms, okay, I will have S sub 2, because I'm adding two terms. 1 plus 2 is 3. That we can see that's my cumulative sums, or we will call partial sums. Now, adding, let's say, 4 terms, S sub 4, 1 plus 2 plus 3 plus 4, I think it's 10. Yeah, that's the fourth one, and so on. That means now we did create a sequence, because now it's commas, we're not adding them, because we don't want to add, we don't want to multiple the values. That means 1, and then 3, if I add 2 terms, if I add 3 terms, 6, 10, 15, 21, that we can definitely see the same thing that we just did through the formula. It's huge, right? It's infinite. Okay? That means this becomes very large, and we will call that this infinite series is divergent. Okay? We will have the same terminology, but let's wait for next slides. Always when you end up with very big number, infinity, of course, we will call divergent. No finite sum. The finite sum doesn't exist. Okay. That's what I did. Yeah. This cumulative sum means the partial sums. That means we actually accumulating, but through the partial sums. S sub 1 means adding 1 term. S sub 2 means adding 2 terms. 3 terms. S sub 4, 4 terms, and so on. In general, we will have S sub n. The first term, second, third, and so on, up to n. That means this is actually the partial sum. Okay, and we can see still no infinity is involved. If I would like to check how this expression behaves at infinity, of course I have to apply infinity instead of n. That means this is my, one more time, S sub n, and I will check, we can see this underneath, how S sub n behaves at infinity. That means if this partial sum at infinity exists as a finite number S, that's the finite number, then we will call that this is the sum of the infinite series A sub n. All right, as we can see, maybe we don't know. So far, we just got the huge number, infinity. But we never know. We know that sometimes the functions, the expressions at infinity, we may have a finite number. They can behave as a finite number, even if we expanding everything to the infinity. Okay? We remember the improper integrals. it's not, of course, it's similar concept, but we remember the integral from 1 to infinity 1 over x squared, which theoretically means like the area under the curve, and infinitely, like the region is like infinite, right? And do you possibly remember that? What was that limit? Limit, of course, but integral. The integral was convergent to, I think most of you attend the session, 1. We don't have to exactly know the value. The most important is that it's convergent. Okay? That means something like that, because we constantly adding terms, and we may have a finite number. Okay. Yes, the partial sum just create a new sequence. We know that from the previous slide. And let's say, and partial sum. Okay, that's me now. Another information reference page. Let's read the sum of the infinite series. If the sequence S sub n, we know that's the partial sums, is convergent to S, is convergent, and the limit exists as a real number, okay? That means that's actually the same thing, because how can we check that it's convergent? The limit must exist. Okay, the limit at infinity, the behavior at infinity. That means that's the same thing. Convergent to S. Then the series A sub n is called convergent. That's what I was referring to, this terminology. That means having not only n terms, infinitely many terms, we may have the finite number. That means now we may notice infinity, it exists as a finite number. That means this is the sum of the series, and we will call that it's like convergent to that number, because I can keep adding and adding and adding terms, but the sum is not going to be greater than S. Always extremely close to S. That means this is the sum of the series. And otherwise, if we get in huge number, or sometimes we can't even get infinity, like we will get some weird things that completely undefined, we will always call divergent. Okay, that means the series is divergent. Convergent if the finite number exists, divergent otherwise. Okay, let's keep moving. You can ask any question, of course. One more time, I apologize for my voice. Probably my practice with Kasia, if I decided to do the short video, probably will be with that voice, but hopefully will be still helpful. Okay. That means this is the explanation. The sum of the series is the limit of the sequence of the partial sums. And this means that adding sufficiently many terms of the series, we get as close as we like to number S. We approaching. The series is convergent to S. Really, really close. That's the reason that we're saying the infinite series, the sum is S. Okay, and one more time, I have this summary. That means this is S, the sum of the infinite series. How can we get this? We have to compute the limit of the partial sum. Okay, and that's the same thing. That means the limit, and all of the terms we can try to add together. Of course, we have to use some formulas, because we still have like this, like the infinity is involved, right? That's when we have to find the formula for the partial sum. Okay. That means let's try to do first exercise. Let's take this. We will start to add the terms of the series. 1/2 plus 1/4 plus 1/8, 1/16. And you probably notice that the denominator is the power of 2 2 to the power of 1, 2 to the power of 2, 3, 4, 5, and so on. I mean, I can, oh, actually, before I wanted to do the formula, because I can rewrite like that, starting from 1, ending at infinity. That means this is my infinite series. And what I will try to look at these sums, yeah, the partial sums. That means if I will take just one term, of course it's 1/2. If I will add 2 terms, right, the partial sum s sub 2, 1/2 plus a quarter, 3/4. Okay, let's keep adding. I did the math for you. That means we don't have to be worried for the lots of fractions. S sub 3 means adding 3 fractions, 1/2, 1/4, 1/8. And common denominator 8, 7/8. And then S sub 4, adding 4 terms, 15/16. And now, as mentioned before, you can see we did create a new sequence, 1/2, 3/4, 7/8, 15/16. And do you possibly see a pattern, which means a formula for the sequence, which this will be the formula for the S sub n, the new sequence, which is the partial sum. Okay, let's see. If n is 1, I have 1/2. If n is 2, right, that means for n1, I have 2 to the power of 1, I can say. For n2, let's look at the denominators first. Okay? Can you see the denominators? 2, 4, 8, 16, which actually almost the same like this. That means, what do you think? What will be in the denominator, the formula for S sub n? What shall I put? This is defined for n3, this is defined for n4, and so on. That means, what do you think? What shall I put in how the denominators behaves? Yeah, I'm just trying to look at the patterns. That's what mathematics is about. We have patterns, we have some shapes, some connections, and we're trying to make the formula. 2, 4, 8, 16. Oh, how would you define this? 2 to the power of, 2 to the power, 2 to the n power, right? Because it's 2 to the power of, and this much. 1, 2 to the power of 2, 2 to the power of 3. Can you hear me? I know that my voice is weird, but maybe you can't hear me. No, you can hear me. Okay, you just quiet today. Okay, okay, it's okay, it's fine. Maybe you lost your voice. I don't know. But I can promise I didn't attend the game, the Penn State game, because sometimes you're losing the voice after the game. I'm not this type of person. I mean, I do attend some of the games, but I didn't attend, and I just got sick. Did you attend the game? Did you go to the game? The white, how do you call it? White night? No? Maybe you're not the University Park students, because we do have in this classroom University Park students. Do you know what I'm talking about? Wow, nobody's responding. Yes. Oh, no tickets. Okay, white out. Thank you for helping me. Yes, because the stadium. Okay, no tickets. Okay. Oh, yeah, okay. Thank you, Zach. Yeah, okay, thank you. Thank you for sharing some information. Now I know that I have students in my classroom, because sitting and talking to the laptop, it's weird. I'm in Southeast Georgia. Okay. I know, because we do have University Park students, but mainly we have the West Campus students. Okay. I was just curious that maybe, of course, with my husband and my 2 boys, our 2 boys, they watched on TV. That means I saw the stadium and it was beautiful. But do you know the score? I don't know if you follow. I'm not really a football. Yes, yes, exactly. Oh, yes. Because actually, I didn't even watch until I think because it was too late. And then in the morning, I checked the score, and my son wasn't happy. I mean, he's still in high school, but he really supports Penn State. I know, 1 point. Okay. That's mean, yeah. Hopefully, you didn't. Yeah, you have your voice. But I just got, yes, I just got C. Okay, let's come back. That means can you see that this is the idea to get, yes, to get the formula. 2, 4, 8, 16. Now, like in order to, I mean, we have to do the same thing on the top. Okay? And what do you think? How the numbers on the top in the numerators are related to its denominators? The denominators. That let's see, if I have 2, here I have 1. It's just 1 less. Exactly. That means I have exactly the same number, but 1 less. Really good. Yeah, okay. That means we lucky, we got the formula for the partial sum. And this is 1 more. Yeah, this was for 5. Okay. And then we do have the formula. Really good. And now, actually I have on my other slide, but we may try to find how this formula, because this is my S sub n, behaves at infinity. And you can probably tell me limit as n goes to the infinity 2 to the n minus 1 over 2 to the n. Do you think you know that limit? We can compare. Actually, do you remember the L'Hopital rule? Because I didn't hear. Sometimes I watch the session, but this week the 6.8, I believe, this was covered by Dr. Bank. Did he talk about like the growing rates of the function? Yes. Okay. Good. Because that's really helpful. Okay. That we can see we do have a leading function 2 to the n. This is 2 to the n. That means exactly the same function. No coefficient. I mean coefficient is 1. I think this is simply 1. Okay. That's what I was gonna use like comparing the growing rates. Right? Like for example, can you tell me that this will be just the limit since I'm talking about. Let's say e to the x over x to the power of 100. Can you tell me that limit? It's definitely infinity over infinity, which we may use the L'Hopital rule, but probably 100 is just infinity. Thank you, because the exponential function grows much, much faster than any power function, even if 100. And if denominator is winning, always infinity. If this will be upside down, the numerator will be, what I said, no. If the numerator is winning, always infinity. If the denominator is winning in terms of the growing rate, always 0. Okay, that means just some review. Okay, that means we do have function, 2 to the n, and this is the same thing, 1. That we can see, we can keep adding 1 over 64, 1 over 128, and so on. I can keep adding the terms, and my sum will be never greater than 1. Okay? This is the sum of the infinite series. I can say this is equal to 1. I mean, convergent to 1. Let me say this. Convergent means like approach. Okay? Convergent to 1. Okay? And I have just numerical values. Yeah, we can see like this will be the partial sums. That means adding 1 term, adding 2 terms, 3, 4, 5, 6, 7, 25 terms. We can see 0.9999, and I can keep adding the terms. I will never get value greater than 1. Okay. And just what I did, just the confirmation. As we can see, this infinite series is convergent. Oh, it's convergent to 1. Convergent to 1. Okay, that means what we will do now. Of course, we did get some pattern, we did get some formulas, but I can tell you it's not always as nice and easy to get the formula for the partial sum, because that will be like really like perfect situation, right? I can look how my partial sums behaves, and then I can have the formula, because that was nice. That was really nice and simple. Yeah, and then I can compute the limit. We good with limits. We know that we can adopt all of the properties, all of the laws of the limit of the function to get to this limit. Yeah, that means I can tell you this process is not always easy, but we still have to figure out. And we will have lots of tools, different tools. Okay, that means now let's start. One of the really important series is the geometric series. You probably remember geometric like progression, and this will look like that. Okay. Having a term, first term, okay, A, in order to get the second, I will multiply by the number R. And then again, taking the second one, I will multiply again by R to get the third one, and again, and again, and again, right? So we will call A the first term, and that number R we will call a common ratio. And why this is common ratio? Because if I will take the second term and divide by the first one, which is AR over A, I will always get R. Okay? Or I can take any like a successors. I can take any two terms, they are next to each other. A sub 3 over A sub 2. This is R. Or maybe A sub 100 over A sub 99. I will always get that common ratio. Okay? And that means we can see each term is obtained from the preceding one by multiplying it by the common ratio. That's what this is, and we call geometric series. Let's find a sigma notation. That's when we can see, because the first term doesn't really hold R, that means we will call that R is taken to the power of 0, 1, 2, 3, and so on. That means for n1, yeah, this is term defined for n2, and so on. For n3, because we're starting from 1. That's the reason that this exponent must be 0 for first term. And it is 0 if I put n minus 1. 1 minus 1. Now, when I substitute 2, the second one, 2 minus 1 is 1. Everything works. And then if I would like to create the third one, 3 minus 1 is 2. That means everything works. This is defined for 4. This is defined for 5, and so on. And this one is actually defined for just for n. Or I should have, okay, I will leave it because I should have I additional index, additional letter. Okay, that means this is just n. Okay. Also, what we can have, sometimes, this is still like, yes, I am introducing geometric series, but also I want you to be confident with the sigma notation. We may play with this number, the beginning. That means, let's see what we can do. I can put 0, right? As I mentioned. Let's define the sigma notation starting from 0. That means when I'm putting from 0, I have to make sure that my first term, yes, the first term will be R taken to the power of 0. And it is R taken to the power of 0. And then the second term will be defined for n1. Right? I can write this because this is, sometimes you're asking, especially for the web assign, always please remember, you have to make sure what is the starting point, the initial value. That means this is the same like this one. And then I will say this is defined for n0, this is defined for n1, for n2, for n3, and so on. Okay? That's using this formula. And I think I have one more. I just picked the random number 3. We may also like put any value, like let's say I will ask you to, let's define the sigma notation starting from 3. The same what I'm doing, I have to make sure that my exponent R is taken to the power of 0 for the first term. That means I have to have n, because n, the first n will be 3. 3 minus 3 is 0. Yeah, that means this one is defined for n3 as the first one, n to the power of 4, n to the power of 5, n to the power of 6, 7. Okay, but we can see, using all of them, I always have the same output. Yeah? It results with the same exponent, powers of r. And we still call this a sub 1, a sub 2, a sub 3. It's still a first term, second term, third term, and so on, even if the n values doesn't really correspond. The original one corresponds, because the red one is like the original. It's a typical geometric series formula, but you may have any. Okay, yeah, this will be important that's important information. Okay, now let's actually try to deal with this. I can show you this, and that's also important slide. Yeah? The geometric series is convergent. Yeah? That means the sum will exist as a finite number if the common ratio, the absolute value of the common ratio, is less than 1. If I rewrite without the absolute value, this is equivalent that the common ratio is between 1 and negative 1. But we can see just the fraction, less than 1 or greater than negative 1. If the common ratio is from that interval, then my infinite series has the sum. Okay? It's a finite number. And what we have, I'm providing for you the formula. I can show you, I do have a proof of this formula. Actually, this page and this page, but we will not go through. It's too many, it's like proof. If you will take maths, I think it's 311. That's the proof, like the math, like the class about just proving everything, then you will probably go through things like that. That we don't really have time. I mean, you can check, I'm providing for you, but you have to believe me that that's the correct sum. That means this is the sum. It's not even like the partial sum, it's just the formula for the sum. Yeah? But remember, we can use this formula if and only if the common ratio is from negative 1 to 1. If the common ratio is outside this interval, we will end up with huge number. The sum will be divergent. Okay? That means that's important, because we will always say, okay, oh, that's the geometric series. Yeah? Of course, we have to recognize, and then we will check the common ratio. Okay? We will check the common ratio, and then we will, if the common ratio is between negative 1 and 1, we will put to this formula and done. Okay? Geometric series, that means a little bit different. We don't have to deal with the partial sums. We have everything. Yeah? Okay, that means let's do a first exercise. Hopefully you remember everything from that slide. That's the proof. That's the second page of the proof. And that's my exercise. Is the series convergent or divergent? And the series looks like that. Summation from 1 to infinity, 2 to the power of 2n times 3 to the power of 1 minus n. Of course, it's a little bit messy, right? We can't have nice, easy life. Yes, we have to. Right. That means, first of all, I can tell you that how can you recognize that this is the geometric series? Let's come back for now. This is the geometric formula, right? The geometric series. And you may notice that n, the quantity n, it's placed in the exponent only. Because we may have different formulas, like we may have the formula, let's say, from 1 to infinity, and I can have 2 to the n times n, for example. Yeah, something like that. Or maybe a little bit less obvious. 2 to the n times 1 over n. Yeah? That means even if n is placed in the exponent, I still have n like outside the exponent. That means this is definitely not the geometric formula. Yeah? If n is placed only in the exponent, no other n's around, and no addition, no subtraction, then this is the geometric series. We may still have addition of 2 geometric series or the subtraction of 2 geometric series, but that's different. Right? But that's how you can recognize that it's the geometric one. Okay, that's what I recognize. And what we can do, since I know that is the geometric one, because n is only in the exponent, I need my first term, and I need my common ratio. Okay, and we do have two ways to find the common ratio, and I will show you two of them. Okay, the first term is just a sub 1. That means I have to take the formula, because this is a sub n. I have to take this formula, and instead of n, I have to put 1. Can you help me? I will change the color for you. I'm just putting 1. You can probably compute faster than me. 3, 1 minus, and instead of n, 1. That means what is the first term? It is 4. 4, 3 to the power of 0 is 1. It is 4. Thank you. That means just in case if the common ratio is less than 1 or greater than -1, we will use the first term. Okay, now the common ratio. The common ratio, I can compute the second term and I can divide by the first one. Do you remember? That's the easiest way. I mean, the most obvious way, okay? Because of course I always have a shortcuts. Yeah, that means we do have a 4. Okay, let's try to compute on the side the second term. 2, I will use the blue color. Let's substitute 2 instead of n. That means what is the second term? 4, 3 to the -1. Okay, 4 over 3. That means I have to put 4 over 3. Well, we can see that's important. 4 over 3 dividing by 4 means multiplying by the reciprocal. Okay, I think we like that, right? The number is less than 1. Common ratio. Oh, did I make them? Oh, thank you. Oh, wow. Yes, it's not to the power of 2, thank you. Oh, maybe we not so. Okay, let's this is 2 to the power of 4, 16 over 3. Thank you. I think Andrea and Zach. Okay, that means where is my mistake? Yes, thank you. My mistake is here. 16 over 3. Oh, I don't think we are lucky, because this is 4, and we do have a common ratio of 4 over 3. Unfortunately, this is greater than 1. Okay? That means the sum doesn't exist. This is the infinite series is divergent. Okay. But just because of that, we know the common ratio is greater than 1. We really need the common ratio to be less than 1. Okay, but we still learn how to get the common ratio. Okay, 4 over 3, and how to get the first term. We can see so easy. Also, like, since we don't have to compute the sum. Oh, my wave is. I just wanted to. Okay, a little bit better. Also, looking at the formula, I can show you the shortcut. Probably by practicing, you will get this. Since we did realize that is the geometric series, all of the n's are placed in the exponent. Now, how can I get even faster the common ratio? I am looking at this formula, 2 to the power of 2n, 3 to the power of 1 minus n. I am looking at this formula and I'm taking only the numbers which are taken to the power of n. That we can see. I can possibly rewrite a little bit. I can say 4 to the n. Oh no. 1 minus n. Because that 2 which actually I even, that we can see 4 is taken to the power of n, because that was 2 to the 2. 4 is taken to the power of n, and 3 is taken to the power of negative n, which I can even rewrite 3 to the power of 1, 3 to the power of n. Yeah, I'm just trying to rewrite the formulas. Okay? Because this is negative n, that means this will go to the denominator. That means what I see 4 taken to the power of n, and 3 taken to the power of n in the denominator. That means 4 and 3. Okay? Only the quantity. I'm not looking at the other values. This will affect the first term or the second term and so on. But only numbers that are taken to the power of n is 4 and 3 in the denominator, which is 1/3. Okay? That means that's how you can copy these numbers. Okay, I do have one more because I would like to still see the sum. Let's see. Okay, solution. Okay, I can tell you that's the exam type or the quiz type. Yeah, we can see I did copy from the previous years. Okay, determine whether the series, and we will read this, is convergent or divergent. If it is convergent, find its sum. So we can see we may have the sum or maybe the series is divergent. And now let's see. First of all, what I see? First of all, I see the addition. That means I might think, no, it's not the geometric one. But looking like a little bit closer, I have n in the exponent, n in the exponent, and n in the exponent. That means no, this must be the geometric one. And then what I'm thinking, it's the addition of 2 geometric series. That means if you will realize this, you will have to split -1 to the power of n plus 1 over the denominator and addition of the other one, 2 to the power of n minus 1 over 3 to the n. Well, that we can see this is definitely the geometric series, and this is also the geometric one. N is placed in the exponent only. And then I will add together. We can't like combine them together. We will get wrong values. Like the common ratio, I will not know, will not really work. Okay? Okay, that's me. Please remember, yes, we have to split this for 2 fractions, and I mean 2 infinite series. Okay, that means this one is the geometric and this is the geometric. And let's try, I really would like to see if you can tell me right away what's the common ratio for this one. Do you think you can tell me? Look at the numbers taken to the power of n only. Oh, Robert, yes, we have to, Keith, we have to be really careful, right? Robert, almost correct. We may see -1 to the power of n, and I see 3 to the power of n in the denominator, okay? Thank you, and Keith answered correctly, but yeah, good try. Okay, that's the common ratio. Even negative, we may still have negative. And I think this works because this common ratio, I can maybe do this way. It's between -1 and 1, right? That means this is definitely the geometric series is convergent. And we will use the sum. The sum is defined as a over 1 minus r. Yeah? This is the must formula. We have to know the formula. Okay. That means looking at the formula, I can maybe box using the blue color. We have the r, -1/3. Do you think you can tell me the first term? What is a? A is the first term. We're not really writing a sub 1, but this is a sub 1. Can you substitute instead of n 1, or it's also 1/3? Because we will have -1 to the power, I can compute, I think it is a sub 1, -1 to the power of 1 plus 1, 3 to the power of 1. That means a sub 1 is 1 over 3, the same thing, okay? That means the sum is 1/3 1 minus negative 1/3. Please note that negative. Okay, and who can give me the final number? This will be 1/3 over 4/3. Oh, 1/4, because we will have 1/3 and we will be adding, and 1/3 is cancelled out, 1/4. Okay? Do you see the entire screen? Because do you see that 1/4? Oh, okay. Yes, you see that. Okay, okay. Okay, that means we have 1/4, but we still have addition. Okay? We still have to focus on the other one. I can divide at the moment, but we will add them together. If, of course, if the other one is convergent. Now, okay, get ready for the other one. Who can tell me what is the common ratio? Can you tell me the common ratio? Just 2/3. Yes, thank you. Yes, Robert, Keith, thank you. Because I see 2 to the power of n. Negative 1 is other exponent. That's not 2 to the power of n. And I see 3 to the power of n. Really good. 2/3. Another good news, because we will get convergence. Convergent, and let's use the same sum. A, 1 minus r. 1 minus 2/3, but who can tell me A for this one? What's the first term? It's A sub 1. 1/3 again. Wow, lots of 1/3, but okay, because 1 minus 1 is 0. 2 to the power of 0, it's 1, and 3 to the power of 1 is 1/3. Excellent. Can you tell me this? Can you simplify this? 1/3 over 1/3. The sum is just 1. And please remember, we have to add them together. Okay? That means 1/4 plus, I can maybe, 1/4 plus 1. Okay, this is the final answer, which I believe is 5/4. I think this is a nice example because both of them are convergent. We did use the formula, but remember about splitting them. That's not the part, addition is not a part of the geometric one. This looks like 2 geometric series. Okay, yeah, do not miss this question. Okay. What we can do, because we do have lots of stuff in this section, and I really would like to cover everything, but let me do another thing, okay? And I will not cover everything, but I will cover most of the stuff. Okay, we're good with the geometric one. We will skip this one, and we will skip this one. Okay, another type. Show that the series is convergent and find its sum. Oh, okay, I should maybe ask you a different way, determine whether it's convergent or divergent. Okay, but we know that it's convergent, and let's try to find the sum. Okay, that means using the tools that we just learned so far, can you tell me, is this also a geometric series? What do you think? Is the geometric one? Of course not. Thank you. Because n is not placed in the exponent, not even once. Because we may have some combinations sometimes. But of course, it's not a geometric one. Okay, that means that tool is not helpful at all. We may try to find the partial sum. Okay, but as I said, it's always risky. Probably at the end of chapter 11, you will know how to look at them. Okay, at the formulas. But for now, we don't know. It's just the first session, the introduction. That means I'm happy that you know that it's not the geometric one. And the other tool that we start the section was the partial sum. That means what we will do, we will try to find the partial sum. Let me check, did I type? Okay, I didn't type. That means what we will do, partial sum will be defined, and let me put I from I equals to 1 to n, because I would like to, we know that n is infinity, but I'm just trying to rewrite this. That means I will have 1 over I minus 1 over I plus 1. That's my formula. And this will be a little bit time consuming, but let's do it. Okay, and this, you will also have to do it on your test. Now I will just find out, I will expand a few terms. That means I will define a first term for I1. That means this is 1 minus half. Let me squeeze it because I want to have room. This is defined not for I, because I have, at the end will be I equals to n. That's the reason that I need I and another like letter. Okay, and then sigma is telling me to add. Then I will have a term for I2. This will be 1 over 2 minus 1 over 2 plus 1, 3. And then I will have a term for I3, 1/3 minus 1/4. Maybe one more for I4, 1/4 minus 1/5. And then let's make a gap. And I also need a few terms from the back side, which I can show you. 1, 2, 3, 4. Okay. The last one will be for n, which is 1 over n minus 1 over n plus 1. 1 before will be for n minus 1. That means instead of I have to put n minus 1. And instead of I have to put n minus 1 plus 1 is just n. Okay. The other one, I'm going like backwards. N minus 2, 1, n minus 2, n minus 2 plus 1, n minus 1. And maybe one more. Hang on, I, n minus 3. N minus 3, and then n minus 3 plus 1, n minus 2. Okay, that means this is the formula. You probably noticed that we have lots of terms that could be cancelled out. Because what we're doing, always the second number in the first term is the same like the first term in the first number in the second term, right? Just opposite signs. That means negative half, positive half. Negative 1/3, positive 1/3. Negative 1/4, positive 1/4. And this will be probably not, definitely cancel out if I will list more terms. As we can see, all of the terms will be gone, not the first one. And the same, let's check backwards. Positive 1 over n, negative 1 over n. Positive, negative, positive, negative, positive, and this will be cancelled out with the term, the other, if I will keep like expanding them. Okay, that means we see that this and this is not cancelled out. That means that's my formula. 1 minus 1 over n plus 1. In order to find the sum, I have to find a limit at infinity of s sub n. How the partial sum behaves at infinity. And can you tell me that limit? 1 minus 1 over huge number, 1 over infinity is 0, 1 minus 0 is 1. Okay, really nice. This is definitely convergent. Infinite series is convergent to 1. Yeah. But this is also the type that it's, even if it looks so complicated, okay, it's actually easy to find the partial sum. That means make sure that you work this example one more time after the session, before the weekly assignments, before the midterm. Make sure that you know like what I did. I'm sure you understand, but try to do it on your own. Okay? And then whatever left is the partial sum. We can compute the limit and it's done. Yeah, that's the sum. Okay. And what we do, because we did have geometric series, also for this one we have a special name. Okay, and I can write the name for you. How can you actually recognize? Definitely you will see the difference. Okay, oh, I'm pointing with my normal pen and you don't see my pointer. You see the difference, right? And what we see 1 over n, and then the other term is almost the same. Can you see? It's just both of them, they came from the same sequence, but they are like next to each other. 1 over n, 1 over n plus 1, 1 over n plus 2, 1 over n plus 3. That means this is the difference of 2 terms which came from identical sequence. Just 1 over n. And this is simply the next number. We can see 1 half, 1/3, 1/3, 1/4, 1/5, 1/6. It's the same formula. That means we have 2 different names. Sometimes you will see the name method of difference, but more like common name for that series is the telescoping sum. Let me write somewhere here. Telescoping sum or series. Yeah, because it's kind of like, can you see, we do have the same pattern. We end up with the first term and the last term. Okay, that's always the pattern. It's like do you know that not the telescope, like the toy for the kids, like the how do you call it? Kaleidoscope? I don't know if I'm pronouncing properly, but you know, like a little tube you can look through, and it's like lots of different shapes are moving. I'm sure you had this toy when you were a child. I think it's kaleidoscope, or maybe I'm. Yes, kaleidoscope. Yes, yeah, I think I am. Maybe my pronunciation is, yeah, Zach, thank you. That means the toy, the kaleidoscope, also operates. I mean, it's built with the same idea. It's kind of like a mirror in the middle. Yeah, it's kind of like a mirror in the middle, and you have like lots of shapes, like different shapes, like some stars, some maybe squares, some triangles, and if they move, you can see the same image here. Yeah, because you can like, yeah, it's like kind of like a tube, but when you move, when you roll this, you can see the shape. That means something. Yeah, I'm just trying to find the logic for the name. That means this name makes sense, telescoping, because it's the same. It's like a mirror image, yeah, of the pattern. Yeah, but this will be the telescoping, or sometimes we call method of difference. But you will not see this method of difference, but telescoping series. Okay, and I think I do. Oh, one thing I don't wanna. I also have that form, which I was not showing you, because if you do, you remember the partial fraction decomposition? If you will see the denominator n and like n plus 1 or maybe n plus 2, then you may think, oh, I should split them for 2 partial fractions, a over n, b over n plus 1. Compute a and b and you will probably get this. That means that's another way to present the telescoping series, which now the method, you don't really see the difference. This is like a typical, like more common way to define the telescoping, but you may also see this. Okay. And I think I have I was typing the solution for you, but we can see the same thing. Yeah. All of the terms are cancelled out. I didn't type everything, but we end up with this and we end up with this. That's the partial sum, and the limit is 1. And you can see I'm just trying to, because having that form, we will not cancel out terms nicely. No, we really have to see the difference. Okay. And yeah, method of difference or telescoping series. Okay, that's, we know the geometric one, we know the telescoping one. Yeah, we know a lot. We have to really practice each kind. Okay. And this is just the geometric explanation. Like this, we can see we will keep adding the sum, and the sum will be not greater than 1. And that's the terms. Yeah, because we didn't really, we had the first term 1 minus 1/2. The second term was 1/2 minus 1/3. We didn't really compute them. 1/3 minus 1/4. As you can see, that's the terms A sub n. But when we add them together, we create this. Yeah, it's just a nice visual explanation. Okay. Okay. Now, that's what we know. We know the geometric one. We know the telescoping series. We also have something like harmonic series. Okay? But the harmonic one, we don't have like lots of different types, or I can't create, because for the geometric series, I can create thousands of different examples. Harmonic one is just this one. Okay? It's just one formula and one name, 1 over n. Okay? And 1 over n means we adding 1 plus 1/2 plus 1/3, 1/4, and so on. Okay? And you see from my instruction, this infinite series, this harmonic series is divergent. And I can show you a little proof. Okay? Hopefully it will be easy to follow. But please remember, because we will use this as a reference. I will always say, oh, harmonic series. 1 over n, 1 over n. Or I will say, do you remember harmonic series, 1 over n, divergent? Or do you remember harmonic, divergent? Because it's so important to know that this is divergent. And from looking at the sum, I will not know, because I'm like adding, okay, 1 plus 1/2 will give me 1.5. And then I will add 1/3, I will add 1/4. That means let's see how the partial sums behaves. Are they creating a finite number? Like we will keep adding terms, okay? We will keep adding terms, but we don't know if the sum is like less than a number. Or maybe the sum actually, it's like accumulate huge value, which will be infinity divergent, which actually that's the case. Okay? But one more time, remember, harmonic series looks like 1 over n addition, and it's divergent. And let's see why. Oh, did I type my sum? I think I typed. Okay, that's what I will do. Since it's a little bit easier to show you, I will just skip some of the sums. That means I will look at the S sub 2, S sub 4, 8, 16, 32, just to see the pattern. That means S sub 1, of course, is 1. S sub 2 is 1 plus 1/2. Okay. Now, S sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. But since the denominators will be too complicated, what I'm trying to do, I'm trying to create, I did create a sum, I changed the numbers a little bit, that is even less. Yeah, we can see this number is less because what I did, instead of 3, I did put 4. Okay, that means if denominator is bigger, the whole fraction is smaller. That means this sum is smaller than my original one. That means my sum will be even bigger. Okay, and now what I have 1/2, and then a quarter and a quarter is another half. That means I have 2 halves. I will keep this way because I would like to see the pattern. Can you see 1 plus 1/2? 1 plus 2 halves. Let's look at this. S sub 8. 1 plus 1/2 plus 1/3, 1/4, 5, 6, 7, 8. And I'm doing the same. I'm creating a sum that is easy for me to find the pattern, but it's different. And it's actually smaller because 3 becomes 4 and all of these numbers becomes 8. This is 1/2, this is 1/2, and this is 1/2. Now I have 3 halves. That means that's how the partial sum behaves. 1 plus 1/2, 1 plus 2 halves, 1 plus 3 halves. And can you see that they will become bigger and bigger? They will become huge numbers. 4 halves, 5 halves, 6 halves, 7 halves. Okay. I have 16. That means I have to add 16 terms. I'm creating a sum that is smaller for all of the 8s, all of the 16s, This is 1/2, 1/2, 1/2, 1/2. Another 4, another extra half, which means 5 halves, 6 halves. And then simply this. Yeah, this is a little bit different because I didn't use n, I used the powers of 2. But the partial sum, it's even bigger than 1 plus n over 2. And 1 plus n over 2 at infinity, of course, is infinity, right? Because it's infinity. That means we don't have to like reproduce this. You have to just, this was just the proof, just to show you that the harmonic series is divergent. Because as I mentioned before, we will use a lot harmonic as a reference, as a tool. I can hang on, do I have, oh no, I can maybe write it down. 1 over n. From 1 to infinity. Okay? It is divergent. Okay, please remember. Okay, geometric one, telescopic one, but that's just the kinds. We may have thousands of examples, but harmonic one is just the one, 1 over n, and it's divergent. Okay, let's do another thing. I think my voice is still not bad. What else? Okay, now, important thing, okay? The theorem, another tool. Let's read this really, really carefully. If the series, summation from 1 to infinity a sub n, is convergent, okay, if it is convergent, then the limit of just the sequence a sub n, it's always 0. Okay, always 0. Because what this means, when the sum exists, do I have, okay, I have a proof, but I can just show you numerically. Like I will be adding terms, the first one, the second one, the third one. And I really want these terms to getting smaller and smaller and smaller and smaller, right? That means eventually at infinity, I'm almost adding, I did write 0, but they are like just tiny numbers, okay? And then we do have the sum. The sum exists, it's convergent. But what is also important, right? If the limit, no, I don't wanna mess up. That means if the sum exists, let's say this way, because we have to know the sum exists, the infinite series is convergent. This means that I'm adding all of the terms, and we do have a chance for convergent because the limit, the terms of the sequence behaves like that. They are zeros. And that we do have a chance for convergent. And in this case, yes. Of course, we did use different, probably, tools, maybe geometric series, maybe telescopic series, maybe just the partial sum, because we may do this sometimes. And we proved that it's convergent. And another conclusion is it's convergent because because the limit, the behavior at infinity of a sub n is 0. Yeah, because that makes sense. But please remember, which now is my point, the converse of this statement, it's not true. Which what I mean, I don't want to even write. If the limit of the sequence is 0, okay? If the limit of the sequence is 0, we can't conclude convergence of the series. If the limit of the sequence, this is sequence a sub n, the behavior of the sequence at infinity is 0, then I don't know, maybe this is convergent, or actually could be divergent. That means, what is the point? The point is, if it is convergent, the limit must be 0. Oh, no other limit, because if the limit is different, like let's say the limit is 5, then I will be like adding 5 plus 5 plus 5. Of course, I will create huge numbers. That's not convergence, okay? That means if the infinite series is convergent, the limit is always 0. Okay? But if the limit is 0, which means the terms are getting smaller and smaller and smaller, then we don't know. We may have convergent, or we may have divergent. And do you think, can you give me an example of divergent series with the limit of the terms being 0? Do you think you can tell me? What about this one? From 1 to infinity, 1 over n. Can you see this? Do you recognize this one? I can write harmonic series. That's what I said. It's really important, because let's look at this limit of the sequence, which is 1 over n, 1 over 1, 1 over 2, 1 over 3, 4, 5, 6. It's definitely 0, but it is divergent. That means, please remember, if the limit of the terms is 0, we may have convergent, but we know nothing. We don't know, like, we know nothing about convergence. We still have to refer, we still have to use different tools. Okay? That means that if the limit is 0, we know nothing about convergence. But if it is convergent, we can always say limit is 0, always. Oh yeah, that's no other option. But harmonic series has the limit 0 of the sequence, but is divergent. Okay. Proof. Now, probably it's the same what I just said. The converse of this theorem is not true in general. Because if the limit of the sequence is 0, we cannot conclude that the series is convergent. No. And of course, harmonic is the perfect example. Okay? My typing is a little bit 1 over n, it's divergent, but the limit is 0. Yep. I have to, this is a sub n. Okay, that means one more time. Let me come back. Do you understand this statement? Because I have 1 or 2 problems, exam type question, and I would like you to answer. One more time. If the sum exists as a finite number, S, if it's convergent, then the limit is always 0. Okay? Ready? Now, one of your first questions this week. Do you think you can give me the correct answer? If the series a sub n, the summation from 1 to infinity is 15, then find the limit of this. Limit at infinity. 0. I'm not, okay. I think I'm not asking just for this. Okay, I'm not asking this is 0. That means, Jesse, you probably answered this. I know, because I really make this that means this is correct. Yeah, this is correct. Yes, Zach, that's the answer. Because what the point is, this number, 15, could be any number. This 15 is telling me nothing. It's just, no. It's giving me the message. It's giving me the message that the infinite series is convergent. Okay? This just means that it's convergent. If it's convergent, the limit of a sub n is 0. That means this is 0. 3 over 6 is 1/2. Okay? Do not, what will happen if I will put 15, 18? The answer A. A is not a good answer. Okay? Because we can't put 15. No, I will erase this. We have to think that this limit is 0. Okay? That means that's the way. I can put any number, 15, 150, 1.5, doesn't matter. It's just the message for us that the infinite series is convergent. And then the limit of a sub n is 0, and then I have additional values, 3/6, 1/2. Good, okay? That means we can see if we know the concept, so nice and easy question. Let's look at one more. Another question that you may see. If the infinite series a sub n equals to pi, find the limit at infinity. Cosine of a sub n over a sub n plus 2. What do you think? What is this limit at infinity? Who can give me the answer? I can give you a minute. Yes, Jessie said A, correct? Because what we have to do, again, 0, not pi. Cosine at 0 is 1, 1/2. Because again, this is the information that the infinite series is convergent. I can use any number, but I'm not using that pi. No, convergent. And if it's convergent, the behavior at infinity must be 0. Must be 0. Okay. Okay, that means definitely don't miss these two questions. We always ask because it's such an important thing. Yeah, that means it's 1/2, not which answer will be this one. And that's the mean option, not this one. No. We're not using that pi. Okay, and then what I have a few notes. Yes, we do have two sequences, the partial sum and the sequence of the terms. We know that, but okay, I also have this. Do you think it's too long, or can I cover one more thing, the last thing? Okay, then actually I will cover everything, even with my how do you say, froggy voice. Okay. Because this is also important things, and it's kind of connected what we just did with that theorem. That's mean, let's actually do this. Yeah, you don't typing, it's okay. That's mean you want to go. Okay, I promise like no more than 10 minutes, okay? But let's stay focused. You can always rewatch the session, okay? And you can, or maybe you can leave the session now if you had enough, and you can watch later, okay? I can let you do this, because you attending the session with me, which I love it. Okay, that's me now. Probably you realize I'm repeating like all of the stuff that we learned. That's when we did learn the geometric series, we did learn the telescoping series, we did learn the harmonic series, and then we had this theorem, okay, that we know that if it's convergent, then the limit is 0. Now, what we will also create, we will create a list of tests, like how to determine whether the infinite series is convergent or divergent. Because we will be not as lucky always that we will have the geometric property, we know what to do. Nice formulas, everything ready. Telescoping, we can expand, we can cancel out, we can get the partial sum. Or the harmonic, of course. Easy and known, proved and known. But we may have complicated formulas, which you will see, we will have complex formulas. And what we will need a list of tests, list of tools. Yeah? We will need a toolbox with lots of tools to prove it that is divergent or convergent. Okay? Most of the tests will not give me the sum if the infinite series is convergent, but that's okay. Will be just enough for me to say, oh, this infinite series is convergent. Fine. I don't have to know the sum. Yeah, because some of the tests will be like not rich enough. Yeah, will be just the test. Okay, it is convergent or divergent. It's okay. Okay, that we will have the list of tests, okay, which you have to start making your reference page. And this is the first one. And we will call test for divergence. The first comment is, look at the name. This test is only testing divergence. we can't say, oh, the infinite series is convergent because of the test for divergence. No, this test is just testing divergence. If something doesn't work, we're not using this test. Okay, and let's read the test. Probably will make sense for you. If the limit of the sequence, a sub n, limit at infinity, does not exist or is different than 0, then the infinite series is divergent. Okay, no more like comments, because we know, okay, infinite series a sub n. I will be like adding terms. The first one, the second one, the third one, and then at the end, if I would like to have a chance for convergence, I have to see 0. Not always, of course, yes, not always. We know this, but if this is not 0, like let's say this limit is like, as I said before, if the limit is 5, different than 0, this means that at infinity, I will be adding 5 plus 5 plus 5. Of course, is divergent. Of course, I'm creating a huge number. Okay, that means that's important. Always, when you see the infinite series, take that a sub n formula and compute the limit. If the limit is different than 0, the infinite series is divergent. End of story. Okay? But now, if the limit is 0, please remember, we know nothing about the convergence or divergence. We have to look for different tests. At the moment, we don't know them. We just know the first one. Okay? That's means, please remember, if the limit is 0, we know nothing. If the limit is different than 0, or even completely undefined, divergence right away. Actually, I can keep that. Okay, that's a test for divergence. And let's look at this one. Show that infinite series, summation from 1 to infinity, n squared over 5n squared plus 4 is divergent. Do you see that it's divergent? Because the limit at infinity of a sub n. Now we have to be quite proficient with the limits. That is the same like 5n squared plus 4. Do you know what is this limit at infinity? It's just the ratio of the same degree function, n squared and 5n squared. Yes, thank you, Robert, 1/5. It's different than 0. What this means, that at some point at infinity, I will be keep adding 1/5 plus 1/5 plus 1/5. Of course, divergent. No chance for convergence. That means this series definitely divergence. And we can say by test for divergence, because we have to state the tests. Yeah. What about this one? Arc tangent of n. Yeah, that's my a sub n. Let's check limit at infinity of a sub n, limit arc tangent of n, limit. Actually, I can rewrite for you, doesn't matter, inverse tangent of n. Do you know how inverse tangent behaves at infinity? Of course, thank you. Pi over 2, different than 0. This infinite series, everything, diverges. Okay? Diverges by test for divergence, because it's different than 0. Of course, the sequence, the inverse tangent, is convergent to pi over 2. Okay, that means this is convergent, arc tangent of n. Yeah, I will have arc tangent of 1, arc tangent of 2, but at some point I will be adding pi over 2, because these terms are approaching this number. That means I will always create a huge value. right? That means this is kind of like the proof. That means one more time, the sequence A sub n converges. But this means that I will take that value and finite number and keep adding. The infinite series is divergent by the test for divergence. Okay, I think only took me 6 minutes. Okay, thank you very much. That's everything in this section. It's quite long, but it's such a important components of the entire chapter 11. I will try to put more problems, especially for the test for divergence, the geometric one and the telescopic one. Okay, and you can check the practice with Kasia later. I will try to solve like few problems for each type. Yeah? Then you will be prepared for your quizzes and the midterm, of course. Thank you very much for staying with me. Thank you.